Good morning to all of you. In our earlier lectures, we had discussed about electrostatics. I had introduced the concept of charge. We had seen that charge produces an electric field in the surrounding area. That electric field exerts a force on other charges. So if you have similar charges, they are repulsed. If they have opposite charges, they are attracted. So we had seen the laws describing electrostatics. We had also obtained Gauss's law, which helps us to obtain electric fields of charge distributions, and we had discussed in detail the fields produced by different charge distributions. Now we move on to another topic, which is magnetostatics. So if you have a charge at rest, then the electrostatic force on the charge is because of an electric field. When the charge starts to move, then we find that other than this electric field, there is another force on the charge, which is called the magnetic force. So whenever a charge is in motion, you can have an electrostatic force because of an electric field, and also a magnetic force because of another field, which we define as the magnetic field. So this magnetic effects were discovered about 2,500 years ago, when they found that certain pieces of metals attracted other metal pieces, and so the field of magnetism was born. And there have been a lot of experiments by various people to discover laws governing the laws of magnetism and their relationship to electricity. So in this part of the module, we will study things about magnetism, magnetic fields, how magnetic fields are generated, what are the forces because of magnetic fields, and how we can employ them for various applications. So before we start discussing magnetic effects, I want to show you some simple demonstrations of magnetic effects, which many of you may have seen somewhere in during your studies. Okay, so we will start with some magnets, which I am showing you here. This is called a bar magnet, and you can see here there is on the upper side a certain N, and on the other side a certain S. N corresponds to north and S corresponds to south. That's called a bar magnet. There is another magnet here, which is called the horseshoe magnet. N corresponds to north here and S corresponds to south here. And you can have other shapes of magnets. For example, you have a ring magnet here. So you can have all kinds of magnets. Now, for example, I will show you that if I bring this, what is written as N, close to N here, then there is force of repulsion, as you can see here. If I bring it to the pole marked S, it gets attracted. So just like electrostatic forces, which we had seen as having both repulsive and attractive forces, this N attracts S, but if I bring N close to N, it seems to repel this. So there is a repulsive force and an attractive force in these two cases. You may have seen what we call as the magnetic compass. Here there is a magnetic compass here. There is a magnet which is suspended on a rotating fulcrum, and the magnet can rotate, and as you can see, it points along a certain direction. Irrespective of what I do to the system here, when I rotate, the needle always seems to point in one direction, and this is the direction of the magnetic field produced by Earth. So Earth has its own magnetic field, and this magnet gets aligned towards that magnetic field. So when we study magnetostatics, we will study what are the forces and torques on magnets like this, and how these magnets get aligned to different directions. Now, in our early stages of development of electricity and magnetism were considered to be two separate fields. So electricity corresponded to charges, and magnetism was described as fields produced by magnets. Now it was in 1819 when Hans Christian Ørsted, a Danish physicist, who was giving a lecture, and during the lecture he suddenly discovered that magnetic fields are produced by currents. Currents have a magnetic field around them. So just to show you that experiment, I am taking a small battery and I am taking a wire. So what I will do is I will connect the wire to the battery and I will place this near the compass, magnetic compass, and I will show you that this leads to a deflection of the compass. So let me hold the wire close to the magnet here, and if you see the magnetic, see immediately as soon as I connect, the magnetic needle rotates, showing that there is a force, magnetic force on the coil, on the magnetic needle, and that rotates. So this was an experiment which was performed by Hans Christian Ørsted to show that there is a very strong relationship between electricity and magnetism, that currents produce magnetic fields. So what is actually happening, as we will see, is a current propagating through this. As soon as I connect the battery to this wire, there is a current flowing through the wire. That current generates a magnetic field. That magnetic field then affects the needle here, magnetic needle, and the magnetic needle deflects. So there is a torque on the magnetic needle which then deflects. So this was the experiment which was performed by Hans Christian Ørsted a long time ago, and after that experiment, people like Ampere, Faraday, Henry, and all these people did a lot of experiments, and the entire field of magnetism got developed. Now we have introduced the concept of electric fields at that time, and I had introduced a unit. We know that electric fields are measured in volts per meter. So we need to have some unit of magnetic fields, and as I will discuss when we start to look at the forces, I will introduce a unit called Tesla. This Tesla is a unit of magnetic field, and it is named after a scientist, Nikola Tesla, and it's a measure of the magnetic field. Tesla is a very huge unit, so usually we use a smaller unit called Gauss, which is 10 to the minus 4 Tesla. So I will introduce this later on again, and I want to show you that there is a meter here which actually is called the Tesla meter, which measures the magnetic field of any at any point. So I have now here two magnets which are extremely strong magnets, as you can see here. These are very strong magnets which attract each other, as you can see here, very strong magnets here, and I want to show you what is the kind of magnetic fields that these magnets produce. So here is, I put the magnet here, and this is a probe. This probe, at the tip of the probe there is a small crystal which actually measures the magnetic field. Now here is the magnetic field unit on this. You can see here there is a, let me zero the magnetic field here, approximately 0.1. So MT corresponds to millitesla, and that's almost 0 millitesla here. So if I bring this close to the magnet, as you can see here, the magnetic field increases. It's measuring the magnetic field, and then there is a negative sign here which corresponds to a certain orientation of the magnetic field. If I take the sensor on the other side, you see there is a positive value of magnetic field here, and you can see the magnetic fields are quite strong here, something like 100 up to about 100 millitesla. So these magnets are very strong magnets, and they produce typically hundreds of millitesla. Earth has about 10 microtesla magnetic field, and these effects are very interesting from and they actually unify electricity and magnetism. And incidentally, there are naturally occurring natural living organisms which use magnetic fields for navigation. For example, there are bacteria called magnetostactic bacteria which have tiny magnetic crystals within them which help them to orient themselves along the direction of magnetic field, and this they use to navigate into the earth because they want to go into regions with deficient oxygen contents. Similarly, there are birds like pigeons which are understood to be using magnetic fields for their navigation. For long distance migration, birds use magnetic fields as one of the sensing agents to direct themselves. Similarly, there are ants which seem to use magnetic fields for navigation on the earth. So magnetic fields are very, very important aspects, and we will in this module study how the magnetic fields are generated by current carrying conductors, what are the forces generated by magnetic fields, and what are the applications of magnetic forces. Now I must mention here that we had in electrostatics, we had introduced the concept of electric field as a vector field. So we say that if you have a charge, this charge produces a field surrounding itself, which is called the electric field. Then if you place another charge here, stationary charge, then this electric field is exerting a force on the stationary charge, either an attractive force or a repulsive force, and that leads to the electrostatic force between these two charges. Similarly, we will introduce the concept of magnetic fields. So if you have a current carrying conductor, if you have a conductor which is carrying current, then this current carrying conductor generates a magnetic field surrounding itself in the surrounding medium. That magnetic field then can affect a magnet like a magnetic needle here, or another bar magnet, or another current carrying conductor, and it can apply forces which are called magnetic forces. So just like electric fields, we will introduce the concept of magnetic field, which is also another vector field, and we will study various properties of magnetic fields. Okay, so we just saw some demonstrations of magnetic effects. So now I wish to discuss magnetic fields, how magnetic fields are generated by current carrying conductors, what are the forces that are exerted on other objects. So remember, in electrostatics we had defined the electrostatic force through an equation as follows. So electrostatic, we had defined electric field as E is equal to F by Q. So if you have a charge Q, stationary charge Q, then it is acted upon by a force F. The force per unit charge we had defined as the electric field. This is the electric field. Now, because there are isolated charges in electrostatics, we could define the electric field through an equation like this, but we find that there are no such magnetic charges, or there are no magnetic monopoles. These are called no magnetic charges, or no magnetic monopoles. So we would have to define magnetic field through another relationship, and that is, and actually as I mentioned just a while ago, that magnetic forces appear only on moving charges. So we need to define magnetic field through another mechanism. So suppose I take a charge which is moving in some direction, then let me try to find out what are the forces acting on this charge. So suppose I have a region, in this region I have a magnetic field, for example a magnetic field produced by a magnet, or a magnetic field produced by a current carrying conductor, and in that region I move a charge. So let me assume that all objects around it are neutral, so there are no electrostatic forces on this charge. Now we find that there is a force still acting on this charge because of its motion. Now what are the properties of these forces? We find that as I change my direction of motion of the charge, along one particular direction there is no magnetic force. So if the charge moves, for example in this direction, suppose I have a charge which is moving like this, then there is no force, magnetic force, but if it moves like this, there is a particular force acting on the charge. So there is one special direction I find along which if I move the charge, there is no force, there is no magnetic force. If I move the charge along any other direction, then there is a force acting on the charge, and that force depends on, so suppose this is the charge, this is the direction in which F was 0, 0. So this is velocity. If I move like this, it may happen that I will find there is a force acting on this, and that force depends on this angle phi between the direction in which I have 0 force and the direction of motion. And I also find that the force is perpendicular to the direction of velocity of the charge and to this direction of 0 force. So this force which I see acted upon by on this moving charge is not only perpendicular to this velocity vector of the charge, but also to the direction in which I had found that the force was 0. So we define a magnetic field B, usually written as B, along the direction in which, so the vector B is a vector which is oriented along the direction in which the charge found no force. So that's the direction of B vector. So this is the direction of B vector along which the charge there was no force on the charge. And we define, so we then propagate, suppose this is the direction, I now propagate perpendicular to this direction, this is perpendicular, and I define the force, I find the force as F is equal to, so I find certain force acting on this moving charge, and as I mentioned, this force is perpendicular to the velocity vector and also the B vector. And so I define a magnetic field, magnitude of the magnetic field as B magnitude, which is defined as B is equal to mod of the force. Let me write a B subscript, tell me it's a magnetic force divided by Q times V. So the force acting on this moving charge is, so I measure the force acting on this moving charge when the charge moves perpendicular to the direction in which I found the force had been 0. So in this direction I find the force, and the magnitude of the force divided by the charge which is moving multiplied by the velocity of this particle I define as the magnetic force. So in terms of a vector field, so this is the vector magnetic field FB vector magnetic force is defined as Q B cross B. The magnetic force FB, vector magnetic force FB, is equal to Q times V cross B. Q is the charge of the charge which is moving. V is the velocity vector of the charge, and B is the corresponding magnetic field. So as you can see here, if the velocity happens to be along the magnetic field, V cross B becomes 0 and the force becomes 0. Along other directions, the force is finite. So if the angle between the velocity vector and the magnetic field is phi, so if I have a magnetic field pointing like this, and if I move like this is the velocity and this angle is phi, then the force, magnitude of the force is equal to Q V cross B magnitude, which is equal to Q B V sin phi. So at phi is equal to 0, the force becomes 0. At phi is equal to 90 degrees, the force becomes maximum, which is QVB, and that is the way we have defined the magnetic field B. So magnetic force depends on the angle between the velocity vector and this magnetic field, and varies like this, QVB sin phi. So let me take an example. So suppose I take a magnetic field. So let me take a coordinate axis x, y, z. So let me assume that this is the direction of the magnetic field, and let me assume the charge is moving in the xy plane at an angle phi with the magnetic field. So there is a plane. I define the xy plane as the plane in which contains the velocity vector and the magnetic field. So I can write the magnetic field B as B times j cap. The velocity has two components. It has a component along x axis and a component along y axis. So I have V sin phi I cap plus V cos phi j cap. So the velocity vector is a vector. So V sin phi into x I cap plus V cos phi j cap. So the magnitude of the force, magnetic force, is Q V cross B, which is equal to Q V sin phi I plus V cos phi j cross Bj, which is equal to now Q V B sin phi into I cross j, which is nothing but Q V B sin phi k cap. J cross j is 0, so this component does not contribute to the force. The only component that contributes to the force is the component along I cap. So Q V B sin phi, I cap cross j cap, which is k cap. So this force, as you can see here, is acting perpendicular to both the velocity vector and the magnetic field, and is oriented in a direction which is actually the cross product of v and b. The magnitude of the force depends on the angle phi, and of course the magnitude of the force also depends on the charge and the velocity. Also notice that depending on the sign of the charge, the force is either positive or negative. So if you have a positive charge, the force is along k. In this equation, if the charge q is positive, the force is along k cap. If the charge is negative, it's along minus k cap. Now what is k cap? K cap is this direction. So one has to use what is called as the right-handed rule for calculating the direction of the force on this moving charge. So the charge velocity is like this, the magnetic field is like this. So if I use the right-handed rule, so I take my hand from I take my right hand with the 4 fingers pointing along the velocity vector and move it towards the magnetic field direction, and the direction of the thumb tells me the force acting on a positive charge. So I take a movement from the velocity vector to the magnetic field. The direction of the thumb tells me what is the direction of the force. Now this is called the right-handed rule, and this is also sometimes referred to as the right-handed screw rule. For example, here I have taken a screw. There is a nut here and there is a screw here. So if I look here, if I rotate in this direction, if I rotate, so let me take a screw like this. If I rotate in this direction, the screw is moving forward. If I rotate in the reverse direction, the screw is moving backward. So this rotation in this direction gives me a force like this. So if I take the screw like this and I rotate the screw from the velocity vector to the magnetic field, the direction of motion of the screw gives me the direction of the force. So this is called the right-handed screw rule. So I can either think in terms of a right-handed screw rule or in terms of a right-handed rule. So which means that I show my 4 fingers along the velocity vector, rotate the hand towards the magnetic field, and the direction of the thumb shows me the direction of the force on a positive charge. The force on the negative charge will be exactly opposite. So the force is perpendicular to the magnetic field. This is very different from what you saw in electrostatics, where the force was along the direction of the electric field. So let me compare the two forces, the electrostatic force and the magnetostatic forces. So we can see here so let me take an example. So let me take a charge of 1 microcoulomb, which is equal to 10 to the minus 6 coulomb, a magnetic field of 10 millitesla, and let me assume the charge is moving at a velocity of 10 meters per second. So the force is equal to, and let me assume that the velocity is perpendicular. So this is the magnetic field and the charge is moving like this. That's 90 degrees. So Q V B, which is equal to 10 to the minus 6 coulomb into 10 meters per second into 10 millitesla, which is equal to 10 to the minus 7 Newton. That's the force acting on the charge. So if I have 10 microcoulomb, which is moving in this direction here, positive charge, then the direction of the force, as you can see, is V cross B. So I take my right hand from the direction of V to B, and the thumb is pointing downward. So if the charge is positive, the charge will be pushed downward because of the magnetic force. So that's an example which tells me. Now I need to define the unit of this magnetic field. So SI unit as I mentioned before, it is Tesla. This is after the scientist Nikola Tesla, 1857 to 1943. So 1 Tesla is so I have to define the force in terms of magnetic field, the magnetic field in terms of force. So 1 Newton by 1 Coulomb into 1 meter per second, which is also 1 Newton by 1 Coulomb per second into 1 meter, and Coulomb per second is current. So this is nothing but newtons per ampere meter. Coulomb per second is an ampere, that is the unit of current. So 1 Tesla is actually 1 Newton per ampere meter, and that is the unit of magnetic field, Tesla. And as I mentioned to you, Tesla is a very large unit, so we also define a much smaller unit called Gauss. So 1 Gauss is equal to 10 to the minus 4 Tesla. So that gives you the unit of magnetic field. So let me give you some indication of the kind of magnetic fields found in various situations. So if you go to the surface of a neutron star, the field is 100 million Tesla. In one of my early lectures, I had mentioned about trains which are super fast, called magnetic levitation trains. In those trains, we use magnetic fields of the order of 5 Tesla. So these are trains which are floating because of magnetic forces, and they can run at very high speeds. Magnetic resonance imaging is a very important instrument in medical field, and this uses a strong magnetic field, and the typical magnetic field is about 1 Tesla. Near a small bar magnet, which we saw a little while ago, the magnetic field is about 10 millitesla. The Earth's magnetic field is about 10 to the minus 5 Tesla, and there is a magnetic field in the interstellar space and that magnetic field is about 10 to the minus 10 Tesla. So you see a very large range of magnetic fields, right from 10 to the minus 10 Tesla in the interstellar space to near the surface of a star like a neutron star, where the magnetic fields can raise to 100 million Teslas. So it's a very large range of magnetic fields, and so you can generate very strong magnetic fields using some of these concepts that we will discuss. So we now introduce a law which will tell me what is the magnetic field produced by a current carrying conductor. This law is called Biot-Savart law. Named after 2 scientists, John Baptist Biot, 1774 to 1862, and Felix Savart, 1791 to 1841. So they introduced this law, which will help us to find out what is the magnetic field generated by a current carrying conductor. Now please remember, we have discussed in electrostatics that when you have a charge which is stationary, it produces a field which we call the electrostatic field, and that field then affects any other stationary charge. So this is electrostatics because the charges are stationary. Now we do not have magnetic charges, so we only have currents, and so in a similar fashion we find that a steady current, a current which is constant in time, does not change with time, will produce a magnetostatic field, that is a magnetic field which will not change with time. Now just like electric field E being a vector field which is a function of both position and time, magnetic field is also a vector field which is a function of position and time. And the magnetic field which is produced by a steady current, that means I take a wire and I pass a constant current through the wire, this constant current will generate a time independent magnetic field in the surrounding space. That magnetic field can then affect other magnets or other current carrying conductors or other charges, and as we have seen, if there is a charge near a current carrying conductor and if the charge is not moving, then there is no magnetic force on the charge, even if there is a magnetic field, because velocity is 0. So we will introduce this Biot-Savart law. So we consider a wire, let me consider a wire which is carrying current. So let me consider a wire like this which is carrying current I. So I want to find out what is the magnetic field at some point P. So for this what I do is I take a small element of length here, dl vector, which is along the direction of the wire, and let me draw this line to be along this direction. This is the tangent to the wire at that point, and let me join this. So this is r vector, and let me call this theta. So this current carrying conductor means what? There are charges flowing through the conductor, and as we have seen, a moving charge will produce a magnetic field. So this moving charge in this, which is current here, produces a magnetic field. So we will define the magnetic field produced at the point P due to the small current element as given by mu 0 by 4 pi I dl cross r by r cube. So the magnetic field produced by a small current element dl vector is given by I mu naught by 4 pi I dl cross r by r cube. R is the distance from here. This is not a unit vector, so if I want to write in terms of unit vectors, I must write like this: mu 0 by 4 pi I dl cross r cap by r square. So just like the electrostatic field, this is also an inverse square law, 1 by r square, and it depends. It's a vector field here, and it depends on this quantity dl cross r. So a small current element dl produces the magnetic field which is oriented along the vector direction of dl cross r, and this quantity here, this is introduced as a constant of proportionality. So mu 0 by 4 pi is a constant of proportionality. And mu 0 is called permeability of free space. We had introduced epsilon 0 in electrostatics, permeability of free space. Here we introduce another quantity called mu 0, which is the permeability of free space, and this quantity has a value mu 0 by 4 pi. This mu naught by 4 pi is defined to be 10 to the minus 7 Tesla meter per ampere. So that's by definition. The constant mu 0 by 4 pi is 10 to the minus 7 Tesla meter per ampere, and mu 0 is a constant of proportionality. So just like a stationary charge produces an electric field in the surrounding space, a current carrying conductor produces a magnetic field, and this small element of current dl carrying a current I. So I is a current flowing through this wire, and so this small element of current is I times dl vector. That current element produces a magnetic field here dB vector, which is mu naught by 4 pi the current times dl cross r by r cube. So just like a electrostatic field, we have now defined a magnetostatic field in terms of current and in terms of the small current element. Now I want to make a comparison between the electric and magnetic fields, as we have seen here now. So comparison, let me put a comparison here, both E and B fields are long range. So they can act at very large distances, the electric and magnetic fields, they are long range forces. Both of them decrease as 1 by r square. Both of them satisfy an inverse square law. Both obey principle of superposition. Which means that if you have two current elements producing two magnetic fields at a point, then the total magnetic field in the presence of both current elements is the sum of the magnetic fields produced by each individual current element. E field is produced by a scalar charge, which is the charge, while B field is produced by a current element. I dl, a vector. E is along the line joining the charge and the point P, while B is perpendicular to the plane containing R and IDL. Also, the magnetic field B depends on angle between IDL and R vector. So these are some points which you may remember. Both electric and magnetic fields are long range fields, so they have effects over very long distances. Both decrease as 1 by r square, both of them are inverse square law. Both the fields obey principle of superposition. This is very useful to calculate magnetic fields produced by different current distributions. Electric field is produced by a scalar quantity, which is the charge, while the magnetic field is produced by a current element, which is a vector, I dl vector. The electric field is along the line joining the charge and the point P where you are calculating the electric field, while the magnetic field is perpendicular to the plane containing the R vector and the current element IDL. And finally, the magnetic field depends also on the angle between the current element IDL and R vector. Now incidentally, we may note that epsilon 0 mu 0 can be written as 4 pi epsilon 0 into mu 0 by 4 pi. 4 pi epsilon 0 we have seen is 1 by approximately 1 by 9 into 10 to the power 9, and mu 0 by 4 pi is 10 to the minus 7. So this is equal to 1 by 9 into 10 to the power 16, which is equal to 1 by 3 10 to the power 8 square, and this is 3 10 to the power 8 meter per second is nothing but the velocity of light in free space. So this is nothing but 1 by c square. So it's important to remember that c is actually equal to 1 by square root of epsilon 0 mu 0. The velocity of light in free space is related to the electric permittivity of free space and permeability of free space through this equation, and that's a very important equation. We'll come back to this later when we discuss Maxwell's equations. Okay. Now I want to calculate magnetic fields of current distributions. So let me take the following example. I want to calculate magnetic field on the axis of a circular loop of current. So I have a circular loop which is carrying current. Okay, so let me call these axes. This is x axis. Let me call this x axis. This is y axis, and this is z axis. So I orient the axis at the center of the current loop. So that's a current loop which is carrying a current. And using Biot-Savart law, I want to calculate what is the magnetic field along the axis of this current loop. We will be able to find this through integration of the Biot-Savart law. For points off axis, it is not easy to calculate, and we will restrict ourselves to calculating the magnetic field along the axis of this circular coil, a circular loop of current. So how do we calculate? So I take some point here where I want to calculate. Let me call this point P. So what I need to do is I need to calculate the magnetic field produced at this point by different current elements. This element produces a magnetic field here, this current element will produce a magnetic field here, this current element will produce magnetic field here. So I take all current elements in the circular loop, calculate the corresponding magnetic fields here, and add them vectorially. Please remember, magnetic field is a vector field, so when I add the magnetic fields, I must be careful in adding them vectorially. So I calculate the magnetic field from all the small elements of currents and use the superposition principle to sum them up vectorially to calculate the total magnetic field. Now remember, we had this Biot-Savart law, dB is equal to mu naught by 4 pi I dl cross r by r cube. So if I want to calculate the current due to this current element, I draw a line like this. This distance is r, and this is I dl. This small element is I dl. This is the magnetic. This is the r vector. This r vector. So remember, this magnetic field at this point, because of this current element, it is perpendicular to both the dl and this r vector, and it is given by this equation. Now please notice here that dl and r are always perpendicular because of the orientation of, because I am choosing myself to be along the axis of this circular loop. So dl cross r magnitude is always equal to dl r. R is the distance from here to here, and the direction of magnetic field is perpendicular to both. So let me draw another figure here to show you the orientation of magnetic field. So let me take the xz plane. So remember, the loop, the current loop is along this direction. So the current is coming out from here. I draw a point here, and the current is going back into this. So that's the tip of the arrow, that's the back of the arrow. So the current is coming out of the paper here, and current is going into the paper here. So that's my point P where I am to calculate the magnetic field. So when I, because of this element, so this is r vector, dl vector. So dl cross r. So dl vector is perpendicular to the page. So the vector perpendicular to dl will be in the plane of the paper, and that vector has to be also perpendicular to r vector. So the magnetic field produced by this will be, now I must use the right-handed screw rule. So the current is going coming out of the paper, and I rotate towards r, and I get the magnetic field direction as this. This is the magnetic field produced by this current element at this point. This is perpendicular to the current element which is coming out of the paper, because B vector lies in this plane. It is also perpendicular to this vector, this r vector direction. So if I call this theta, So B vector now has both components along the x-axis and the z-axis in the exact plane. Now it is interesting to note, because the problem is very symmetric, so it is interesting to note that if I look at the current element which is exactly diametrically opposite on the other side. So for example, in this figure, if I am looking at this current element, I look at this current element. If I look at this current element, there is another current element here. For a current element here, there is another current element on the other side. So what I do is, for a current element here, this is the magnetic field. For this current element, which is now current is going inside, the magnetic field happens to be exactly the same magnitude, but in this direction, because this current is going inside the paper and the r vector is here corresponding to this element. The magnetic field happens to be in this direction, that angle is also theta. The current element dl and the distance are exactly equal for both cases. So the magnitude of the magnetic fields at both cases are the same. So let me call this, sorry, dB and dB. So this is the dB current magnetic field produced by this small current element dl here, IDL. This is the magnetic field produced by another current element IDL here, and what you notice is they subtend the same angle with the z-axis and they are oriented like this. So immediately I can see that this particular magnetic field has a positive component along x, this magnetic field has a negative component along x having the same magnitude but oppositely directed. So what you see is the x components of both the magnetic field produced by this current element and this current element will cancel each other, and the z components will add to each other. So please just see this problem. Because of symmetry, I find, because I am looking at the magnetic field along the axis of the circular loop, this current element produces a magnetic field oriented like this in this direction, oblique to the in the xz plane. This current element produces the magnetic field in this direction. The angles theta are exactly the same, because all the, as you can see from the triangle here, and because of this, the x component of this magnetic field produced by this is exactly equal and opposite to the x component of magnetic field produced by this current element. So what you will find is, if you take the circular loop, for every current element there is exactly another current element in the opposite, diametrically opposite point, which will produce another magnetic field whose x components will cancel. So similarly here, this component will cancel with this component. So all the components of magnetic fields perpendicular to z axis will cancel each other. So this one and this one will produce magnetic fields whose components perpendicular to z axis will cancel. Similarly, this one and this one will produce magnetic fields whose components perpendicular to z axis will cancel, and so on. So all that will happen is all the components along the z axis will add to each other, and the components perpendicular to z axis will cancel from each other. So all I need to do is, first thing I notice is the total magnetic field produced by this circular loop must be along the z axis, and I can calculate the magnitude of the magnetic field now. So let me write this as d bz is equal to, so I had written this equation here, mu naught by 4 pi. So I have mu naught by 4 pi I dl r by r cube, was the dl cross r is dl times r by r cube, and I am looking at the z component, which is cos theta. So this is the magnitude, this is the total magnitude of the magnetic field, and its z component is cos theta. The x components cancel each other. So that is the magnetic field here, and cos theta I can calculate. So if this is the radius of the coil and this distance is r, so cos theta, so this angle is theta. So notice that this line is perpendicular to this line and this line is perpendicular to this line, so this angle is also theta. This r vector is perpendicular to this, the magnetic field is perpendicular to r vector, and this line is perpendicular to this line, so that angle is theta. So cos theta is nothing but capital R by small r. So dBz becomes mu naught I by 4 pi r square dl into r by r. So, I can write the magnetic field not I r by 4 pi r cube to dr. And if you notice, so if this distance is z, then r square is equal to r square plus z square. So, I can write, I can use this formula in this equation and write this as mu naught I r by 4 pi into r square plus z square raised to the power 3 by 2 dr. So, that is the magnetic field produced by a small current element dl. Suppose this is element. Now, I must integrate over all the elements of the current which is along the circle. So, I will integrate this to get the total magnetic field dB Bz is equal to mu naught I r by 4 pi r square plus z square raised to the power 3 by 2 integral dl, and integral dl is nothing but the circumference which is 2 pi r by 4 pi r square plus z square 3 by 2 into 2 pi r. So, this gives me mu naught I r square by 2 times z square plus r square 3 by 2. So, I can write the total magnetic field. So, if this is my current loop, this is z axis x y. So, the total magnetic field along the axis at a point on the axis at a distance z from here is equal to mu naught I r square by 2 times z square plus r square 3 by 2 k cap. Okay. So, we can see we can actually calculate the magnetic field at any point along the axis, and it depends on the distance from the plane of the circular loop through this equation. So, if I were to plot B magnitude versus Z, what you will find is as you can see here, there is Z square plus R square in the denominator. The maximum magnetic field will appear when Z is equal to 0, and as Z increases to either positive or negative side, the magnetic field will decrease, and so you will get the magnetic field going like this. So, this is the peak of the magnetic field which is given by. So, magnetic field at the center of the loop magnetic field B is equal to mu naught I by. So, this is my current carrying conductor loop here. So, at this point the magnetic field is pointing like this. So, as you can see here again we have the right handed screw rule here. So, if I take my nut like this, so if I rotate like this in the direction of the current, I see that the screw is moving towards me, and so that is the direction of the magnetic field. So, the right handed screw again rule gives me the direction of the magnetic field. So, if I put my fingers along the direction of the current, I get the direction of magnetic field. So, magnetic field is pointing along the k direction here, which is given by this. Now, so this is for a single loop. If you have multiple loops, you can actually calculate. So, if you have n loops closely wound, the total magnetic field will be at the center will be mu naught n I k cap. So you can actually increase the magnetic field by changing putting a larger number of loops in the coil, and you can get a strong magnetic field. So let me take calculate one example. So let me take a loop of radius 20 centimeters. Number of turns is 100, and the current I pass is 5 amperes. So the magnitude of the magnetic field at the center is given by mu naught N I by 2R, which is equal to 4 pi 10 to the minus 7 into 100 into 5 divided by 2 times 0.2, which is approximately 1.57 millitesla. So you can see if you have a 100 loop coil with 20 centimeter radius, you will get about 1.6 millitesla at the center of the coil, and as you move away from the center on either side, the magnetic field will decrease. And notice also that the direction of magnetic field, so if in this loop here, here the magnetic field is like this, and the magnetic field is pointing away from the loop here. So the current is flowing like this. Now let me leave a small problem to you. Calculate the magnetic field at the center of a circular arc of wire of radius r carrying current I. So you have current carrying circular arc, so that is the center, and let me assume this angle is phi. So that is an arc. So this is just the arc. Instead of a circle, I have an arc carrying a current. So what is the magnetic field here? Please calculate this. Thank you very much.